So let's start with vitamin B9, folate. The name of folate is very descriptive of where folate comes from. Folate comes from foliage. This means that we have to act like koala bears, right? We have to eat our foliage. When your mother said, eat your greens, I'm telling you, our moms understood biochemistry. They had an intuitive understanding of this. Eat your greens. That's where folate comes from. It comes from foliage. Now, does everybody eat your proper vegetables? Okay, good. I'm preparing for Dr. Robinson tomorrow because she goes into some really good discussion about basic diet. So folate, we take up folate from our gut. We have receptors that can bind and internalize folate. We bring it inside the body. Folate is not useful to us. There's nothing about folate that we can work with. So we have to convert the folate into two steps, dihydrofolate and then to tetrahydrofolate. Okay? So it's a two-step redox reaction. So these are both reductive mechanisms, and all we're doing is we're just slightly modifying the folate into this tetrahydrofolate. And I will abbreviate that FH4 for tetrahydrofolate. It's also abbreviated in text, and I think first aid uses THF for tetrahydrofolate. Now, the enzyme is absolutely critical that you know this, and this enzyme is dihydrofolate reductase. Now, let's continue on with this process, and then I'll come back to the importance of this enzyme, why it's important to know this enzyme. So with tetrahydrofolate, the next thing that we're going to do is we are going to convert this into methylene tetrahydrofolate. I'll use the first aid designation THF. Now, what this step involves is a conversion of serine to glycine. Now, what's important for you to know here is that we are taking tetrahydrofolate and we are adding one carbon. So one carbon atom is going to be added to the tetrahydrofolate to form the methylene tetrahydrofolate form, and we're getting this one carbon from serine, converting it to glycine. So this is involving one carbon transfers. So we're taking one carbon, we're charging up this molecule, and now this molecule is available for doing the one carbon biochemistry. So methylene tetrahydrofolate now becomes a cofactor. And probably the most important one carbon transfer that this is doing is it is converting deoxy-UMP to deoxy-TMP. So this is simply adding a single carbon. So remember when we were talking about pyrimidine biosynthesis, we took our pyrimidines down to orotic acid, and then we put that onto the ribose sugar, and then we had the base structure that we were going to do all of our modifications to make all of our other pyrimidines. And remember I said that the ring is made, and all we had to do is modify the structure around the ring to make the other pyrimidines. Here is how we take DUMP and we turn it into thymidine monophosphate. We are simply adding the one carbon of methylene tetrahydrofolate to the TMP. And what comes out of this reaction is tetrahydrofolate. And so as long as we have an adequate supply of folate, we can perform this reaction, converting tetrahydrofolate into methylene form, continue making our deoxythymidine monophosphate from uridine monophosphate. Now this deoxy-TMP will be converted to deoxy-TTP, and now we have one of our bases to do DNA synthesis.
Dr. Orlando?
Yes.
The image you have in your slides had to go into DHF instead of THF.
DHF to THF.
So 5,10 methylene THF goes back to DHF.
No, to DHF.
Is that correct, or is your drawing correct?
No, I believe that's incorrect. Yeah, I pulled this one off the web because I thought it was a nice condensation of everything we're talking about. So this actually goes back to THF, not DHF. So we're just recycling the tetrahydrofolate. Okay, so now, why is dihydrofolate reductase such an important enzyme for you to know? This is a drug target. And that drug is methotrexate. Now, methotrexate originally was discovered as a drug that would inhibit cell proliferation. So if this drug inhibits cell proliferation, it's doing so by blocking the conversion of folate into tetrahydrofolate. If we block this conversion, we reduce the amount of tetrahydrofolate. That means we reduce the amount of methylene tetrahydrofolate, so we reduce the conversion of DUMP to DTMP. So essentially what we're doing with this drug is we're inhibiting the formation of thymidine. If we inhibit deoxythymidine, that means we'll inhibit DNA replication because we inhibit our precursor and we inhibit cell proliferation. So this turns out to be a very, very, very good anti-cancer drug. Now, unfortunately, this is not selective for cancer cells. So this is going to perform this inhibition of this reaction in all cells. And so typically what that means is that all cells will be compromised in their cell proliferation. So what does this mean to cells of the immune system? Immune system, immunocompromised individuals, because they cannot replicate their immune cells and mount a proper immune attack. What does this mean to individuals with their GI tract? We're going to lose a lot of our integrity of our GI tract because remember, we lose about a quarter of our entire GI lining every day, so we need a lot of cell proliferation to keep up with that. Okay? So methotrexate is a good anti-cancer drug because it can kill the cancer, but this is one of those old type of anti-cancer therapeutics that basic scientists, we love, because you as physicians ask us, come up with a drug that we can stop the proliferation of cancer cells to treat our patients. And we came up with one for you. Now this is where medicine and basic science separate. You're interested in saving the patient. We're interested in killing the cancer. Do you see the problem there? If we kill the patient, oh well, it's not our problem, right? This is the problem with these old anti-cancer drugs. These things are freaking bombs. It's a nuclear option, okay? So this is the importance of targeted cancer therapy in the future, but it's very effective. So methotrexate is still used in the clinics for an anti-cancer drug because anti-cancer drugs are still in development for targeted therapy, but there's actually a better use for it now. And this is for anti-arthritic drugs. So this was discovered after the anti-cancer properties were established. And the reasoning for this is that if you inhibit cell proliferation, you could potentially reduce the inflammatory response in arthritis. And so what rheumatologists have discovered is that if we take the methotrexate and we were able to reduce the dosage of methotrexate, we can avoid all of those nasty side effects, but we can provide relief for arthritic patients by reducing their inflammation. So all this is the same drug, but we've just titered back the effect of the drug. Okay? The drug is still inhibiting dihydrofolate reductase, but by inhibiting only a portion of it, we're able to sort of target the most highly proliferative cells, being the immune system. Now, this is also used in Crohn's disease. Now, why would this be beneficial in Crohn's patients? What is the basis of Crohn's disease? What is causing Crohn's? Is it a structural problem? Is it an injury? Is it a metabolic imbalance? Is it an inborn error?
It's immune-mediated.
It's an immune-mediated reaction. Yeah, so Crohn's is caused, remember, it's that trans-tissue inflammation, so it goes through the entire wall, and this is an increase in inflammation. And so again, having this anti-inflammatory effect with reduced dosage, it turns out to be able to dampen the effects of Crohn's disease. Okay, so this is one of actually the first-line therapies that can be tried for Crohn's disease. If you don't want to go to the full biologics, you can try an anti-inflammatory therapy. And one of them is this low-dose methotrexate. Okay? So there is a good example of medicine. What is the most important information for you to take away from this entire biochemical pathway? Right here, dihydrofolate reductase is inhibited and regulated by methotrexate, and that inhibits the formation of thymidine. This enzyme, of course, is thymidine synthase. And so the inhibition of thymidine by blocking this first step enzyme will lead to reduced DNA synthesis. And then the dosage effect of methotrexate will affect grossly cell proliferation by blocking DNA activity in cancer cells, or low dose will depress the immune system to cause an anti-inflammatory effect. Okay, so there's the medicine. So, good example. Would I ask you about tetrahydrofolate being charged up to methylene tetrahydrofolate and using serine as a precursor? Is that something that would be fair to ask you? No. Because that piece of information, there's no medicine right there. The medicine is right here at dihydrofolate reductase, and if you block this, you block single carbon transfer and thymidine formation. Okay? So that's kind of how I'm starting to tailor questions. That's my revolutionary way to approach it. Okay, so now, there's two other directions that we can take the methylene tetrahydrofolate. So one direction is to make what's called formal tetrahydrofolate. Methylene form to formal, and then the formal tetrahydrofolate, which is simply not a tuxedo, formal. Wow, you guys are really serious today. Not formal, but it's formaldehyde. And so this methylene form is a nitrogen with a carbon and a nitrogen. And so we're going to convert this into a formaldehyde form. And what this is used for is purine synthesis. So again, it's the same principle. It's one carbon transfer, but the substrate, the cofactor here, is going to be formal tetrahydrofolate. Okay? So now, here's the power of methotrexate. We're not only inhibiting deoxy-TTP formation, but we're also able to inhibit, because we're reducing the methylene form, we're also able to inhibit and dampen purine synthesis. And that's the power of methotrexate. Now, the other direction it can go, the methylene tetrahydrofolate can go and form a methyl tetrahydrofolate. And this is simply taking this single carbon bound to two nitrogens, and we're going to convert it into a methyl group. Now, here's where we get into problems. In order to perform one carbon transfers, the carbon which is being donated by either methylene or the formal forms of tetrahydrofolate have to be good, going back to chemistry, good leaving groups. Good leaving groups mean that that carbon has to be bonded very weakly. Okay? So a carbon in this form with two bonds coordinated by nitrogen is an exceptionally weak bond. Okay? So that makes this a good donor of carbon. So simply what that means is this reaction of thymidine synthase can take that carbon very easily off of this structure and add it to UMP to make TMP. It's very easy to extract that carbon and put it on that molecule. Now, the formaldehyde group, is a little bit stronger bond, but this still represents a good donor of that single carbon. So it means the same principle as the thymidine synthase. The enzymes for purine synthesis can take this carbon off of the tetrahydrofolate, put it onto the purine rings, regenerating tetrahydrofolate. Everybody's happy. Now the methyl group, methyl tetrahydrofolate, methyl groups are incredibly stable. So the methyl tetrahydrofolate is not a good carbon donor. And that simply means that the enzymes for biosynthesis are unable to extract this carbon off this molecule and add it to the substrate. Now, what happens is that eventually, if you have a limited amount of folate, so let's say your folate intake has been reduced, so you have the beginnings of a folate deficiency, vitamin B9 deficiency. That means that all the folate in your body is going to have to perform all of these reactions. Given time, eventually all of the tetrahydrofolate will end up in the methyl tetrahydrofolate form. This is called the methyl trap hypothesis. And this is a result of a partial folate deficiency. So, what does that mean? If you have complete complement of folate, if you're eating your leafy greens, and you have a continuous supply of fresh folate, you can continually supply these pathways of methylene and formyl and keep your one-carbon transfers going. If this is cut off, so you have a folate deficiency, then all of this methylene and formyl, as they're being processed, eventually the flow of all material here is going to end up in the methyl form with that deficiency. Now, how do we resolve this methyl trap, which means all of your tetrahydrofolate is trapped into this methyl form that is not a good carbon donor? Okay? So this is where we have to go through another processing event to generate a one-carbon transfer to be able to alleviate this problem and regenerate tetrahydrofolate so that we can resupply the one-carbon transfers and keep that cycle going. So now let's start out with methyl tetrahydrofolate. What we need to do is convert this back into tetrahydrofolate so that we can continue supplying the substrate for the one-carbon transfers. Now, the way we're going to do this is we're going to introduce vitamin B9, which is cobalamin. Vitamin B12, cobalamin. Vitamin B12 is going to be a recipient. So this particular reaction here with B12 is able to extract this methyl group and generate a methyl form of vitamin B12. So all we're going to do is transfer this methyl group to vitamin B12. Okay? Now, why is this reaction important? For two reasons. First, reason one, we can regenerate tetrahydrofolate. This reaction with vitamin B12 will prevent us from having a folate deficiency because we can recycle it. The second one now is that we have to be able to do this. We have to be able to convert the methyl B12 back into vitamin B12 so that we can keep this cycle going to relieve this methyl trap problem. If we weren't able to do this, we would deplete ourselves with B12 and we would end up with a B12 deficiency. So we have to keep this going. So that means that we have to transfer this methyl group to something else. We're going to transfer this to homocysteine. Now, remember, cysteine amino acid, the side chain of a cysteine amino acid is this. So here's our side chain of cysteine. Homocysteine has an extra methyl group on that side chain. We're going to take the methyl group from B12 and we're going to add it onto the sulfur group of homocysteine. And what we're going to end up with is this.
Methionine.
Bingo! Somebody's exercising their biochemistry mojo. So there's methionine. 10 points for Gryffindor.
It's not a Gryffindor.
Oh my God. Is he a Slytherin? Okay, so this is the biosynthesis pathway of the amino acid methionine. This is how we make methionine. Now, even more important than that, because we're going to get a lot of these amino acids from our diet normally, here's another problem. We convert homocysteine continuously into methionine, we're going to run out of homocysteine. So that means we have to come back around to generate homocysteine. So what we're going to do is we're going to find a way to take this methyl group and use it to our advantage. And we're going to form this. We are going to add an adenine, the purine base, to methionine, and we're going to add it to the sulfur group. What we're forming here is called S-adenosyl methionine, abbreviated SAM. Where's Sam?
Homeschooling.
He's homeschooling? Okay. Sam, this one's for you. We're going to make SAM. Now, what we're doing here is, for those of you that are interested in chemistry, does sulfur like 3 bonds? Obviously, that's a rhetorical question, so no. Sulfur doesn't like 3 bonds, it likes 2 bonds. So what we're creating here is an unstable sulfur, which means that we are generating a good carbon donor. And here is the carbon, that methyl group on S-adenosyl methionine. So all of this process here of adding this purine base onto methionine is to destabilize this bond right here between the sulfur and the methyl group, to make this methyl group a good donor, just like we saw with the methylene in formal forms. Now, this is a huge 1-carbon donor, okay? So this is going to perform all kinds of wonderful reactions by donating that methyl group. And I listed a few of the reactions here. There's a 1-carbon transfer that converts norepinephrine into epinephrine. There's a 1-carbon transfer that finalizes the form of creatine. Another big one, methylated nucleotides. So when we're performing our methylation reactions on the DNA in order to silence genes, SAM is our donor for these methyl groups. Phosphatidylcholine. This is making our phospholipids for our membrane. That's a conversion of phosphatidylethynolamine to phosphatidylcholine. And then the final one is melatonin. So SAM is an essential cofactor. So if you're deficient in this process, all of these reactions are going to be inhibited. Okay? So now, once we perform this reaction with SAM as a cofactor to donate the methyl group, we generate S-adenosyl homocysteine. Because the form of this is back to this structure. And here's our homocysteine. And so now to get back to homocysteine, we simply remove the purine base. Okay, so now, what does all of this mean in medicine? If we have a folate deficiency eventually means that we will deplete ourselves of our methylene cofactor and of our formal cofactor. So we are going to have DNA synthesis problems because we're not going to be able to generate our bases for DNA synthesis. Eventually, a folate deficiency by just normal excretion of the tetrahydrofolate product, we will now be deficient on methyl formation. And we'll be deficient on transferring that methyl group into SAM so that we can perform all of these important methylation reactions. What if we have sufficient folate in our diet, but we're deficient on vitamin B12? Well, we could perform some DNA synthesis because we can form some bases, but without B12, we're going to be stuck in our methyl trap hypothesis. So as long as we have folate coming in, we can still generate our methylene in formal forms, but eventually we're going to have so much methyl form that we cannot convert that into the methyl B12 form to generate SAM for these important one-carbon transfers. Okay? So now, taking this one step further, before we go there, I found this summary diagram for you, and this thing here is all correct. And it's a real nice compilation for like future step 1 studying to make sure you've got this whole level done right. So I thought that was pretty good. Borrowed from, I give acknowledgments, this very nice gentleman, Gui, whoever that is, published on creativecommons.org. That's really cool. So this is a Creative Commons where somebody can draw a diagram like this and put it out there for free for people to borrow and download. So I checked that out. There's actually quite a few things in there. I have to add my own stuff in there. Be part of the community. Oh, yeah, one more thing.
Take that and make one modification and solve it.
Another point of medicine, homocysteine. So homocysteine is closely associated with elevated cardiovascular risk, okay, for infarctions, for stroke. The direct connection of why elevated homocysteines are associated with this risk is still a subject of debate. But these are some examples of what the research is pointing to. Homocysteine is associated with endoplasmic reticulum stress. So this stress in the endoplasmic reticulum is often due to protein misfolding and oxidative damage. Glutamatergic receptor activation. So hyperactivity, increased influx of calcium. That could be pretty detrimental in cardiac muscle. Elevated homocysteine levels have already also been thought to be part of increased DNA damage. And DNA damage, of course, is going to induce DNA repair. And if that repair mechanism is imperfect, whole series of problems. So this is medicine knowing that homocysteine levels, so if somebody has high homocysteine levels, they are at risk for a cardiovascular event. All of this here that's subject to current research is not really current medicine. This is still research. So what do you need to know? Well, if you have somebody like me at my age come in with high elevated homocysteine levels, it needs to trigger in your head for potential for a serious cardiovascular event. So if I present with a high homocysteine levels, what are you going to do for me? What are you going to recommend and prescribe?
Baby aspirin.
Is what?
Baby aspirin.
Baby aspirin. Yeah, we'll get to that and the icosanoids. So looking at this here, what are you going to recommend to me? What's your thought for treatment? Yeah. You're going to recommend to me that I take folate and B12. Because if I have a high homocysteine level, if this level starts going up, it's because I'm not able to process it to methionine. So the way to relieve this problem is to make sure that I have sufficient amount of folate and sufficient amount of B12. Now, that being said, folate deficiencies are a much greater frequency than B12. B12 is stored typically in the liver, and it lasts for years. We don't have a real good mechanism to dispose of B12. Care of another problem with this methyl trap, in addition to being folate deficient. Okay. Now, if I'm folate deficient, folate and vitamin B12 deficient, and that's pretty, when you first become deficient in folate and B12, it doesn't really present much clinically. So my homocysteine levels might go up. Can I feel my homocysteine levels going up? No. So I'm not going to go to a doctor and talk to them about this problem. Now, I might show up on a routine exam, and you might take a normal blood panel test, and that's where you would discover the beginnings of a folate B12 deficiency. So where would you see that? You're going to see that in my red blood cells. So if we have a folate and B12 deficiency, we are going to have a reduced amount of tetrahydrofolate, which means we're going to have a reduced amount of our 1-carbon transfers and a reduced amount of our pyrimidines and purine nucleotides. So we're going to compromise DNA synthesis. Now, compromising DNA synthesis, say in my gut, is going to take a while to manifest a problem. Down the road, I'll probably start having some, absorption issues, diarrhea problems, and all that. But something else is going to show up even sooner. And that's in red blood cell production, because we're constantly making red blood cells. The megaloblasts are constantly turning over. We constantly need DNA synthesis. And so here's our normal red blood cell development. We have our DNA synthesis and cell division of our megaloblasts. And then eventually we start beginning our hemoglobin synthesis. And then we pop the nucleus out while we're continuing our hemoglobin synthesis to load up our hemoglobin. And then the last step, of course, is loading this up with iron. So what we will have on here are normal-sized red blood cells with the proper hemoglobin concentration, with the proper iron bound to that hemoglobin. Now, if we have a folate and B12 deficiency, cell replication is going to be compromised. It's going to be slowed. The RNA synthesis is going to continue. We're still going to be making hemoglobin, but what's happening now is that our red blood cells are not dividing and shrinking and becoming that normal size. And so these red blood cells that are put in our circulation are very large. So they have an increase in size because of the compromised DNA synthesis, because of the folate and B12 deficiency. So what's this going to show up like on a blood test? There's two values. One is called the RDW, for red cell distribution width. Now you can imagine if you take your red blood cells and you put them through a sizing measure, a way to measure the size of the red blood cells, what you would see on a graph is cell number. So you're going to count the number of cells that are of a particular size. And if you have uniform red blood cells that have been properly developed, this should be like this. So this is normal. And this simply means that our red blood cells are all of the correct size. The majority of them under this curve are of one size. You've got some that are a little bit bigger, some that are a little bit smaller. Not a real big issue. The key is the distribution width of size is narrow. Now, with megaloblastic anemia, because we have a DNA synthesis problem, what you're going to have is this. Our RDW, our red cell distribution width, is going to be expanded. And that's because now we have cells of various size, especially the large ones here. So that's one of the values. The other one is MCV. I like to call this mean cell volume, because this is the volume of the red blood cells. What the C stands for in the old days is mean corpuscular volume. Because in the old days, red blood cells were called corpuscles. I have no idea where that came from. It's way before my time. So I like to call it mean cell volume. So what you're measuring here is the actual volume in microliters of the cytoplasm of the red blood cell. So based on this red cell distribution width, with uniform red blood cells, you would say that the mean cell volume is going to have a very narrow reference range, and it does. So if your mean cell volume increases, that is an indicator of enlarged red blood cells, which is most likely means decreased folate and or decreased vitamin B12. So that's called megaloblastic anemia, mostly because the red blood cells are large, and you will see megaloblasts in the circulation. The other name for it is pernicious anemia. And pernicious anemia, I think that term ultimately came from a vitamin B12 deficiency. Okay? So again, this is where medicine is. So you can see where the questions would be. If I gave you information on blood tests, if I gave you both MCV or RDWs, you should be able to tell if this is a macrocytic anemia and a macrocytic anemia is simply a folate or B12 deficiency, or as we'll see tomorrow, a microcytic anemia, and that's due to an iron deficiency. Okay, and we'll see that reasoning tomorrow. Okay, now, this next picture here will close the loop from our GI issue. So we're going to go back into the gut now. How do we get normal vitamin B12? Well, vitamin B12 we get from our diet, and the structure of vitamin B12 is incredibly large and complex. It is also very lipophilic, because there's a lot of ring structure to it. It actually has a ring that's even more complex than a heme ring and hemoglobin. But it tends to be very lipophilic, which means that it is going to bind avidly to protein. And we're talking about dietary protein. So it binds so tightly to dietary protein that we cannot get that B12 off of that protein and absorb it. So it enters the stomach. First reaction it sees in the stomach is increased parietal cell activity, decreasing pH because of the acid conditions. So what this is going to do is denature the proteins. By denaturing your dietary proteins, that is going to help try to loosen some of that vitamin B12 binding to it. The next thing we have is pepsin digestion. So pepsin will digest the protein, helping to release more of those vitamin B12. Now, once we start losing this vitamin B12, we have another problem here with the pancreas. So the pancreas is going to put out our enzymes that are going to digest the proteins, the proteases, but all of the enzymes that the pancreas put out are proteins. And so B12 could be absorbed onto these proteins in the pancreas and have the same problem as they entered the diet. So what we're going to do now is the parietal cells are going to be secreting intrinsic factor. Intrinsic factor is going to substitute for the dietary proteins, and it's going to bind the vitamin B12. This R binders, forget that. That's unimportant. The key element here is the intrinsic factor from the parietal cell. And of course, the parietal cell is undergoing active secretion because of the digestive conditions. And so the B12 binds to the intrinsic factor. It's protected from binding to the pancreatic proteases. And then in the terminal ileum is where we have a receptor for the intrinsic factor. So this is an intrinsic factor receptor. So the intestinal enterocyte binds this, internalizes it. It then degrades the intrinsic factor and transfers the B12 onto its carrier in the blood, which is called transcobalamin. That's the carrier for B12 in the blood. From there, it's distributed to all tissues that need B12, which all tissues do. But notice 50% of it goes to the liver, and this is the storage for excess B12. Okay, so that kind of completes the loop when I mentioned way back when, seemed like years ago, that the parietal cell was not only producing acid, but it was also responsible for secreting intrinsic factor. And so that's the use of it here. So now, this process is important to recognize for two medical reasons. One, if somebody suffers from Crohn's disease that's so bad that they have to have an ileal resection, what's their vitamin B12 absorption going to be like? Bad, yeah. You're going to have a reduced capacity for vitamin B12 absorption. And so those individuals are going to need B12 from another route, and that can be an injection. What happens if you have somebody on a proton pump inhibitor? How is that going to affect their B12 uptake? It's still going to bind to the proteins in diet. So now what you're relying on these individuals are the pancreatic proteases to digest any dietary proteins to release the vitamin B12. Okay? So they still will have B12 absorption, but it could potentially be compromised. Now it's interesting, I looked this up a couple of years ago to see if there's any clinical data on people on long-term PPI therapy, do they have B12 deficiency, and I didn't see anything. But theoretically this could be a problem. Probably isn't a major issue because B12 is so long-lived in the body. It's very hard to become B12 deficient. Hence why when most physicians diagnose a problem with megaloblastic anemia, macrocytic anemia, they typically restrict their recommendation to folate intake and not B12 because B12 lasts so long. However, it doesn't hurt to throw in B12.